So the goal of this lesson is to be able to derive rate laws. So we're going to sort of pick up where we left off last day, and then we're going to build upon it. I want to make sure you're very comfortable with, if you change concentrations, a double or triple, what does it do to the rate laws? And then we'll jump right into data and kind of work backwards. So our generic formula is A amount of A plus B amount of B makes C amount of C plus D amount of D. Our rate law may factor in both of the reactants, but we don't use the stoichiometric powers. We have to experimentally determine the powers of each reactant. In theory, one of the reactants could have a 0 power, which means you would drop it right out of the rate law. If B was 0 order, why would you write B to the power of 0? So you just write rate law equals K, which I forgot, times the concentration of A to whatever power it has. If something is first order, an individual chemical, and you 2x the concentration, okay, that will 2x the rate if it's first order, 2 to the power of 1. This is what we're going to have to start looking for when we flip to the next slide. If something is second order and you 2x the concentration, you're going to get a 2, the doubling of concentration to the power of 2 because it's second order. You'll get a 4x change in the rate. So most of the questions you're going to be able to solve by inspection. You won't have to go and write out equations and do math. Okay? But I'll also show you how to solve it what if the concentration goes up 0.674 times. Okay? That won't be as obvious to look at the rate and look at the ratios. So you can always write out one rate divided by another rate and calculate the order for the non-nice multiples. So let's jump into a question and start sort of working backwards. Again, okay, we're going to kind of go this way. What did the rate do? What did the concentration do? And we'll finish up with what is the order. That's why I'm reviewing this, so when we go backward, it's really fresh. So we're asked to determine the rate law given the following data. And this is for fluorine reacting with 2-chloro-dioxide. And we've got 3 experiments or trials, I label them. The first one, the concentration of fluorine is 0.1 molar. The chloro-dioxide is 0.01, and we have a rate. That's going to set our initial perspective. In the second experiment, a controlled variable is fluorine, but the ClO2 looks like it's 4 times bigger, and then we're going to have to look at what happened to the rate. In experiment 3, the second reactant is now a controlled variable, and the first reactant was doubled. And we're going to see what did that do to the rate and determine the rate law from this information. Okay. So what we're trying to build, which this won't be complete yet. So the rate law, the rate equals some constant times the concentration of fluorine gas to some power. Now I'm going to take that question mark out. We're going to figure out what power goes there. Times the concentration of our other reactant. Again, I won't put a question mark in. That's our goal. So we have to go up to our data now and start processing. We're going to look for a controlled situation and a chemical that's changing. we can't deal with both chemicals changing at the same time. We can't figure out the order for any one. So if we start with our first trial, fluorine is 0.1. Okay, there it is as a controlled variable. So we're not going to figure out the fluorine order, but we can figure out the other reactants order. What type of concentration change do we have here? That would be 4x, 4 times bigger. So now we're going to look at our rate. Okay, these are initial rates. You will have to determine these rates in lab situations. So this experiment would have started at initial concentration, it would have dropped and leveled out, and this data is the tangent at the very beginning, the slope at the very beginning. That's where the initial rate came from. So 1.2, okay, is this 4 times or is this 16 times? It is 4 times faster rate in experiment 2 compared to experiment 1. Okay? If you didn't see the number, you would take the second, divide by the first. So 4.8 divide by 1.2. The 10 to the minus 3s are going to cancel. So whether you put them in your calculator or not doesn't matter. So 4.8 divided by 1.2 is 4 times. So our concentration to what power does the rate? Well, that's the x is going to be 1. Okay? This is first order kinetics. Concentration to the power of 1 equals the rate ratio. So for ClO2, we have first order kinetics. Okay. Now we've got to figure out what's going on with fluorine. What is the order to the fluorine chemical? So we have to find an opportunity where the second chemical is controlled. So if we look at experiment 1 and 3, the concentration of chloro-dioxide is the same. So we've got to look at what the fluorine concentration does and the rate. So 1 to 3, this is a double in this case. And then we'll look at the rates. And 1.2 to 2.4, that's a double. So the concentration was a double, and we're to some power, equals the rate ratio, which is 2, so that question mark is also a 1. In each case, we're seeing first order kinetics for both chemicals. Whatever ratio you apply to the concentration, the rate shows up as the same ratio. So first order for each chemical, second order overall would be our kinetics for this reaction. Okay. So this was done by inspection. Let's go through this sort of long mathematically to get the same answer. Okay? You'd only do this if it wasn't obvious. If you had some unusual decimal ratio, you may not be able to do this all in your head. So let's compare the rate of 2 reactions. I'm going to fill in numbers in a second. Okay. I'm going to end up using the first 2 in this example. And I always like to put the bigger reaction, the bigger values on top. If I put the bigger values on top, I'm going to get like 4.2 or 4.8 over 1.2. I'll get like 4. If you put the smaller concentration, the smaller rate on top, instead of getting a ratio of 4, you'll get a ratio of 1/4. The math will work out the same, but you'll have all these fractions. Okay? So I always suggest when you set up your rate ratios, you put the bigger numerical values on top. So in trials 1 and 2, trial 2 has the bigger concentration and the bigger rates. So I'm going to do rate 2 divide by rate 1. So okay. So a rate is always a rate constant times the concentration of your chemicals to some power. Okay. I'm assuming we haven't solved this yet. We don't. We're trying to find X and Y. Okay. I left out my states for the sake of speed. Okay. We'll fill that in for rate 2. Okay. For trial 1, it's going to be K So rate 2 is different than rate 1. The concentrations will be different, but the rate constant is always going to be the same. One of the big reasons of comparing one rate as a ratio of another is it cancels out the rate constant. We don't even have to know what it is to figure out the orders. Okay, we don't know what the rate constant is. So rate 2 is 4.8 times 10 to the minus 3. I'm going to leave my units out just to keep things cleaner. It's not the nicest presented solution, but again, it makes the presentation and the algebra cleaner. Okay. Rate 1 is 1.2 times 10 to the minus 3. Fluorine is in both cases, in both rate trial 1 and trial 2, it's both 0.1. Our chloro-dioxide so we have this sort of algebraic expression. Our K's are going to cancel. We don't know what it is, whether it's 10 over 10, 5 over 5, 100 over 100, we don't care. And we can cancel something else. Okay. We don't know what x is, but 0.1 to the power of x divided by 0.1 to the power of x, these two are always going to cancel each other out. Okay. And this leaves us just y as the only variable to solve for. So our ratio of our rates was 4 equals, I'm going to collect the powers, or our ratios. They're both to the power of y. So 4 equals 4 to the power of y. So y equals 1. We got that first order kinetics we already saw. So obviously you wouldn't do this both ways. You're not going to do it by inspection and see the ratios and then go down and do the math. But this is just another tool for you to use if you don't see the math. You can just set it up and let the ratios just come out mathematically and compare them. If you put the smaller ratio on top, which I don't encourage you to do, the smaller rate, this will still work, but you're going to get 1/4 equals 1/4 to the power of y. And then you've got these fractions. When these fractions don't match up and they end up as decimals on your calculator, you may not see that one fraction is just the square or the cube or the 4th power of another one. And I think it's more difficult. So that's why I always want you to put the bigger ratio, the bigger rate on top, the smaller one on the bottom. A little bit more quickly playing with the rate laws and those powers, and then we'll do another similar example, but we'll calculate the K value. We'll calculate some rates in our next question. Okay. So given a rate law, okay, we're not determining it, we're using it again, trying to make sure we're really comfortable with the meaning of the powers. So rate is a K times second order for A and first order for B. And what would happen to the rate if the concentration of A doubles and the concentration of B doubles? Okay. What would that do to the overall rate? So what is the effect of doubling A? We've got A and B to factor in. If A is doubled, okay, the concentration factor would be doubled, but then it's second order, so we'd have to square that effect. So it's going to have 4 times effect on the rate. And we're going to have to multiply that by what we're doing to B. B is doubled, but it's first order. Okay? I wouldn't expect you to write the 1, but I'm just emphasizing the order. Okay? So this ends up being 2 to the power of 3, or 2 times 2 is 4, times 2 again is 8. Okay? So we're going to see an 8 times increase in the rate of reaction if you double A and double B because of the second order and the first order kinetics. Okay. Using the same rate, what if the concentration of A stays the same, but the concentration of B is 1/2? So it doesn't go up, it goes down by 1/2. So we have to multiply the effect of each concentration. The concentration of A is the same, so that's like 1 times. So squaring that doesn't matter. And then B is 1/2 to the first power, so that would only have a 1/2 effect on the rate. Okay? A isn't going to have any effect. And it wouldn't matter its order if you keep the concentration the same. So one more big question, and then I'm going to have you practice one, and then I have a little bit more to wrap things up. Okay. So we've got some data to take down. I'll just pause for a minute while you grab the key information, and then we got 3 questions to solve. What is the rate law? That's what we did in the previous example. What is the rate constant? Okay. We didn't go and solve that before. Okay. And then C, what is the rate of reaction under a different circumstance? You know, maybe call this experiment 4. Okay. Okay. Which is C, what if those concentrations are in our table? What would the rate be? Okay. So I'm going to scroll. I'm going to hide that reaction because we've got 2 nitrogen monoxide and 2 hydrogen gas, but that's not going to tell us the rate law. So we want question A, rate law. Rate equals K times the concentration of NO times the concentration of hydrogen, and we're going to figure out what powers go there. We're going to be able to do this without any big equations or rate ratios. So let's look for a controlled variable. So the first thing I notice is experiment 2 and 3 have the same concentration of nitrogen monoxide. So we can look at what hydrogen does, solve for hydrogen's order. So 2 to 4, well, that's a double. Don't need a calculator for that. What does the rate do? That's 5 to 10, that's a double. Okay. So the concentration changed was a double to some power equals the ratio of the rates. So first order kinetics. Double causes a double. This is for hydrogen, so we have first order kinetics for hydrogen. Now we got to repeat this and figure out our first reactants order. So we need hydrogen to be a controlled variable. So in experiments 1 and 2, it's a control. And the concentration from 1 to 2 is 5 to 10, so that's a double. And 1.3 to 5, that may not be as obvious. Okay. You may want to grab your calculator and do the ratio. Okay. When you do that, you get 3.8. There's some experimental error. We didn't get a whole number, but that's pretty close to 4. That's the nearest whole number. So we're going to use 4 for our data analysis. So the concentration doubled, but we're seeing about a 4-time change in the rate. So that's going to be second order kinetics would lead to that 3.8. We'd expect 4. It's slightly lower than expected. Okay, so I'm not going to go and get my calculator and do 1.9 or 1.8, whatever it works out to. I'm using the whole number version. Second order kinetics for the first chemical, first order kinetics for the second. So we've answered A. We have our rate law. B, so we want to get the rate. So we want to get K. We're going to rearrange this equation to solve for K, and then we got three options to solve it. I could do experiment 1, because in experiment 1, I know the rate and I know the concentrations. I could solve for K. Experiment 2, I know all the pieces but K. Or experiment 3, I know all the pieces but K. So you could pick any one. I'm going to pick the first one to get the answer. But again, you could pick any trial you want. Okay. In theory, you could do it more than once, but on an exam or an AP exam, don't go and solve it for 2 different experiments unless you're asked to. So I'm going to skip showing my work with the algebra. I'm going to rearrange that for K. When you do that, you get rate divided by concentration, second order for the first reactant, first order for the second. Okay. And I'm going to use trial 1 data to solve this. 1.3 times 10 to the minus 5 moles per liter per second. So again, I'm picking everything from experiment 1 for my B answer. So we had 5.0 times 10 to the minus 3 moles per liter, but I've got to square that, and 2.0 times 10 to the minus 3 moles per liter. And when I throw all that into my calculator, this is actually the easy part, getting the number. I get 260, and then watching the units is the trickier part. Okay, and it's something that I certainly will award marks for having the correct units when you get asked this on a test or quiz. So we end up with moles, molality, moles per liter squared there, and then moles per liter once there. So I'll kind of summarize this and then cancel. We have 3 of them on the bottom, and on the top we have moles per liter per second. I'll put the seconds down below. So we can simplify this a little bit more. We got 1 m on the top, 3 on the bottom. So I'll cancel the 1 out on the top, and we're down to 2 on the bottom. So the units you could express this way: moles per liter squared on the bottom, seconds on the bottom, or what's commonly done in AP or university is use negative powers. So that 2 on the bottom is moles per liter to the minus 2, seconds to the minus 1. So you need to be able to make sense of units written like that with negative powers to show the bottom of fractions. Okay, C, and we're done. Okay, what is the rate under different circumstances? I kind of threw it as circumstance 4 into our table. What is the rate when NO is 12 times 10 to the minus 3 and hydrogen is 6 times 10 to the minus 3? Well, once we know the rate constant, it's just plug everything in and solve. 260 number-wise, I get 2.2 times 10 to the minus 4. We've got 2 m's and a third m on the top. and we have 2 m's on the bottom and seconds on the bottom. So our final units is moles per liter per second, which we would expect for a rate. Okay. This is what you know you're going to get for a rate. So if you made a mistake with units and get seconds squared on the bottom or 2 m's on the top, you know you have a unit mistake to go back and double check and fix. Okay, so let's see if you can solve the next one. We'll summarize the answers. So we've got a reaction on the top. Really is kind of useless to us. It would tell us stoichiometry. We could turn one chemical's rate into another, but that's not what we're doing here. What is the rate law and the rate constant given this data? So very similar to the last problem. So I'll let you work for a bit. We'll summarize the answers. You should be able to solve this one probably by inspection and looking at the ratios and not doing rate 2 over rate 1 or rate 2 over rate 3 numbers. Okay. So just summarizing the answer, the rate law, rate equals K, and we just need the orders. They both come out first order, and we always have a doubling of rates. Either way, they're a doubling, and all our concentrations are a doubling or a half, depending on which way you look at it. Okay. And the rate constant was 0.081 times 0.081. So now, last question of the lesson. I'm going to set this up and let you think about it. What is the rate law is the question. Okay. Now let's go through the data. Okay. So the relative rate for the reaction of 2A and 1B is 1 to 2 to 4. So that needs to be summarized. What is the rate? We don't know the numbers, but we know relative rates. This is sort of our default. When 2 A's and 2 B's react, we had a rate of 1. Okay. We have a different combination in B, and that is the middle number. That whatever happened from A to B caused a doubling in the rates. Okay. For our last experiment, we have 4 times the rate compared to the first one, okay? And we're asked, what is the rate law? So the rate equals K times A and B. And I'll let you look at this for a second and see if you can deduce the rate law given these graphics. So I'm just going to add in the color labeling. So red is A, and the green spheres are chemical B. Okay. So let's see if your thinking was right. Let's analyze from A to B. What's going on in A to B is the green spheres stay the same. So B is our controlled variable. What does A do? It goes from 2 to 4. So A, chemical A, is doubling. And what does the rate do? It doubles. So you double A, the rate doubles. That's first order kinetics for A. Then if we compare A to C, here red is our controlled variable. And green is changing. Green doubles again. So our green is doubling, but the rate goes up 4 times from A to C. So that is second order kinetics. So this is third order overall, first for A, second for B. So for practice on page 42, I debated picking out selective problems. So I said they're all good. You don't have to do them all. A lot of them you can do in your head and maybe not write everything down. So that's why I wanted to leave all of them in. I would make sure you can do the rate 2 over rate 1 and make sure you can do that method and try it at least once. What's next is first order kinetics and the math. And when I say first order, I mean first order overall. Okay? And then we'll look at the math for reactions that are second order overall. That's 2 lessons away from now.